Perhaps the first question about an icebox is, when do we need to use an icebox? In general, we want to use an icebox whenever we are asked to do calculations involving the equilibrium state of a system and we're given information about the initial conditions before we reach equilibrium. For example, if we want to calculate the value of the equilibrium constant and are given the initial concentrations of the reactants and products and one equilibrium concentration, we should set up the icebox. Another common calculation is when we're asked to find the equilibrium concentrations of reactants and products and are given the initial concentrations and the value of K for the reaction. To set up an icebox, we start with the balanced equation for the equilibrium reaction. The icebox is sometimes called a rice box because we start with the balanced equation for the reaction. The box is created with 3 rows for initial conditions, change in conditions, and equilibrium conditions, 1 column for the I, C, and E, and 1 additional column for each reactant and product. To use the icebox, we start with the initial conditions. In this example, we begin with some of each of the reactants, A and B, and no products at all. This is not always true, and the amount of each reactant and product are determined in the particular problem. It is possible that we might start with only products, or with some of each reactant and product. So we enter the amounts of each substance into the appropriate spot in the table. M1 and M2 are the initial concentrations of A and B, and the initial concentrations of C and D are both 0. We enter those values in row 1, the I row of the table. Next, we deal with the changes to each concentration. The changes are related to reaction stoichiometry, with one side positive, that is, increasing in concentration, and the other side negative, decreasing in concentration. These are determined by the stoichiometry of the reaction, that is, the coefficients of the balanced equation, and whether the substance is a reactant or product. Since we don't have any of C or D, we must make some to reach equilibrium. Remember that at equilibrium, there is some of each reactant and each product present. So the amount of each product will increase, and the change will be positive, and the amounts of each reactant will decrease, and the change will be negative. The signs always are opposite for the reactants than for the products. If it is not immediately obvious whether products increase or decrease, you can use Q to determine which direction the reaction moves to get to equilibrium, and deduce the signs from that. Remember that the balanced reaction gives the relative amounts of each reactant and product. The reaction says A molecules of A react with B molecules of B to produce C molecules of C and D molecules of D. If we define X as the change in concentration for a coefficient of 1, then the change in concentration of C is plus Cx. The change in concentration of D is plus dx. The change in A is minus ax. And for B, minus bx. We enter these values in the second row of the table. Notice that we use the coefficient in the balanced equation times an unknown x. We could do other things, but this is probably the simplest way to get the appropriate ratios among the reactants and products. If we know what one of these changes is, then we can determine what they all are by solving for x and using it to determine each of the others. If we do not know what one of these changes is, we have the changes all in terms of x. The equilibrium values are the sum of the initial values and the change. So we can now fill in the third row of the table by adding the change for each substance to the initial value of each substance. Once the form of the equilibrium values is known, if we know the value of x, or can calculate it from an equilibrium value, then we can determine the equilibrium concentrations and calculate K. If we know K, but do not know x, we then substitute those expressions into the equilibrium expression and solve for x. In general, this may be a very difficult problem to solve, particularly if the resulting expression produces a third degree or higher polynomial. On the AP test, however, you will not be required to solve anything higher than a quadratic equation. Two words of caution about applying the solution to the quadratic equation. Remember that x may be the solution to the mathematical equation, but it may not be the answer to the problem for two reasons. First, as in our example, the value of the concentration of C is not x, but C times x. And for the reactants in our example, we need to subtract Bx from M2, for example, to find the concentration of B. So remember to substitute x into the expressions in the equilibrium row to get the actual concentrations. Second, there are two answers to the mathematical equation. Both will solve the math, but only one will make sense in the problem. In particular, even a positive value for x could produce a negative value for the concentration, but it is not possible that the concentration of a substance could really be negative. So always make sure to check that the answer makes sense.